Welcome everyone to Up42's first Ag Tech webinar, where we'll discuss with some of the great minds from across the industry the future of farming, driving crop and business growth with satellite imagery, weather data, and deep learning. First off, we have Sean Malamed and Griffin Williams from Catalyst. Sean is a product marketing manager at Catalyst and has over 15 years of combined education and professional experience developing and implementing remote sensing tech for private, public, and defense applications. Sean specializes in geometric and radiometric correction of optical satellite imagery, as well as automating insight extraction through machine learning and AI. And now I'll turn the virtual stage over to Sean and Griffin for our first presentation, where they will showcase how to analyze crop health and predict crop yield with deep learning. Thanks for joining us today, gentlemen.
Thank you so much, Elizabeth. We're really excited to be here today and to showcase our solutions. So we're very excited to showcase to you a novel technique that leverages analysis-ready data from satellite imagery in order to help analyze and predict the yield of crops using a deep stack of time series imagery. In this case, we're going to be showcasing an example using spot data. So the particular goal of this example that we're going to walk you through is, once again, the idea is leveraging the analysis-ready data in order to evaluate the performance at a particular period in time and predict the yield of crops from a time series of various spot sensors captured over a period of 10 years. The two techniques that we're going to that are going to leverage analysis-ready data in this particular example. The first one on the left is an intra-field anomaly detection. So this is the idea of taking a snapshot in time and understanding how and where within a particular field or an area of interest our crops are performing based against a particular key performance indicator, such as the Ndvi metric, comparing it against a baseline of data captured at the same Julian day or the approximate same Julian day in previous years from our time series stack. And this is done by creating a baseline and comparing our results today towards that baseline to see where we have to perform additional analysis or additional or potential field work, send people to the field. And we can see how we can compare against that baseline. Griffin's going to go into more details and showcase how we can do that and leverage analysis-ready data for that. Now, on the right, we're going to showcase another concept where we actually take the profile of a growing season for a particular field, and we plot that KPI. Once again, we're using an Ndvi in this case, and we plot that over the growing season in order to create a growth profile, and we can compare that growth profile to all of the previous growth profiles from different years. And we can start to use that to understand, based on where we are in this growing season, what is our prediction going to be using regression analysis, such as AI, machine learning, in order to understand how much yield we're going to get if we don't make any corrective action. Now, before we can go and actually perform this kind of analysis, there's a variety of rigorous steps that need to take place in order to get the measurements out of the satellite imagery so we can accurately perform that type of time series analysis. This starts off by first just capturing the satellite imagery. Now, you may not be aware in your particular area of interest, but imagery has been captured all over the world for the last 30+ years. So likely in your area of interest, there is imagery that has been that's been captured for many years and is available in various archives for that area. We then take that stack, and this oftentimes, if we're analyzing 10, 20 years, whatever it may be in our particular stack here, this could be a accumulation of hundreds, if not thousands, of images that we then need to convert to what's known as analysis-ready data. And this is really normalizing and correcting the positions of the images so that when we are doing our analysis that we're going to showcase, we're able to compare apples to apples. And there's a lot of steps. And this is traditionally where 80% of the time is taken. And because for a variety of different sensors, there isn't an automated workflow. It was previously not feasible to do this type of analysis, but now we're going to showcase our automated workflow for this and how we can now quickly create this information product and then extract that or then import that into something like the Open Data Cube in order to then perform a variety of analytics like what we showcased here earlier. So with that, I'm going to hand things over to Griffin, who's going to walk us through an example like this.
Great, thank you very much, Sean. As Sean mentioned, I'm going to show two different multi-temporal analyses using a stack of spot imagery using the normalized difference vegetation index. So on the screen now, we can see an Ndvi growth profile for a field throughout a single year. So we can easily identify some trends in this data, such as where the growing season is in this sort of main kind of larger section over here. But by itself, this isn't particularly useful. But when we have a stack of ARD imagery over a long period of time, we can easily extend this analysis to cover all the other time periods in our data stack. So now we have an example here from 2010 to 2017, where we can, look at these trajectories and establish trends, perform analysis, and then derive those kind of predictive models that Sean has alluded to before. And another type of analysis we talked about was performing Ndvi-based anomaly detection. So this type of analysis highlights areas where the Ndvi value is different from a specified baseline, where areas in green are have higher Ndvi values and red areas lower Ndvi values. But before we can comfortably perform that type of analysis, we need to ensure the data is robustly pre-processed to an ARD format, as Sean had mentioned. So on screen now, I'm showing you the AOI that we were using in the Cape Town region of South Africa. So these red vector layers are the footprints of all the spot imagery that were processed for this analysis. So hundreds, thousands of images, which would previously be too time-consuming or simply unfeasible to do prior to our Catalyst ARD processing technology. And then this little polygon here is representing our area of interest that the analysis was actually conducted over. In Catalyst Enterprise, our ARD processing workflow is broken up into three main sections, all of which can be completely automated: the geometric correction, the spectral normalization, as well as the ARD data packaging. But a lot goes on under the hood within these workflows. So just to give you a better example, I'm going to show you the modular version. So these are all of the pieces that comprise those three main sections. So the geometric correction steps between data ingest all the way up to accuracy assessment map creation are required to ensure that the pixels in your imagery throughout your stack align up to 1/10 of a pixel accuracy using our state-of-the-art super registration technology, which takes alignment a step further than traditional orthorectification measures can. So once we have those data very highly aligned, we then need to spectrally normalize them. So that's where steps 6 through 8 come into play, where we're spectrally normalizing the data to ensure the radiometry is consistent between images that are taken at different times, under different viewing angles, solar angles, from different sensors even, in order to make sure that we're making an apples-to-apples comparison. So the output of this process are surface reflectance products that are corrected for the effects of the bidirectional reflectance distribution function, which is a bit of a mouthful, but they're called N-bar surface reflectance products, and they ensure that comparisons are apples to apples. And then lastly, once we have that data normalized, we can then generate additional metadata files and then package the data so that we can quickly and easily integrate it into an analysis framework such as the Open Data Cube. So I'm going to show you that here now, an example of performing that anomaly detection in using a Jupyter notebook in the Open Data Cube. So as mentioned, all of the data has been rigorously pre-processed in automated fashion, and now we're able to get into the analysis. So I'm just going to start off by loading in all the different Python packages and utilities that I need to use for my analysis. I'm going to define the equation from which to calculate the Ndvi, and then I'm going to build up a query where I take my N-bar spot products that are here from spot 2, 4, 5, 6, and 7. And then I set up, I determine a baseline and I determine an analysis period. And then I'm going to run that cell. So that's my query. And then I can load my mosaic based on that information that I've supplied. So I'm just loading that in now, generating the composites, generating the NDVI layers, and then actually performing the analysis by subtracting the baseline from my analysis period. And then I can plot that and generate this graph or chart, which shows us areas where the NDVI value is lower than our baseline and areas where the NDVI value is actually higher than the baseline, which can be a useful tool for getting an understanding of how your field is performing at a particular point in time relative to a reference period at a similar time. That's a very quick demonstration of the type of analysis that we can do in the Open Data Cube using ARD data that's been generated using Catalyst technology. So with that, I'm going to send it back to Sean.
Wonderful. Thank you so much, Griffin. So I'm just going to do a very quick recap of what Griffin showcased and go into a little bit of detail on that, because there's obviously a lot there with some of the code. So just to do a recap of what we showed here is that we took a variety, a couple hundred different scenes of spot imagery, I believe it's spot 2 through 7, and converted it to analysis-ready data using our automated analysis-ready data workflow in Enterprise, and then put that into the Open Data Cube in order to perform a series of regression or series of analysis, both the anomaly detection and building up the profiles by using simple queries, which is really accessible to a wide, broad audience. So just to recap what we ended up doing, and I think this came in as some of the questions, in terms of what are we performing in terms of building this growth profile? Well, essentially we're creating an NDVI from all of the different images within a particular year, and then we capture for a particular field, whether it's outlined by an object, and we can either capture the average NDVI for that entire field or for a particular pixel, and then we plot this on a graph over time so we can see what the NDVI value. This basically indicates the growth curve. Now, this would be important for a particular field growing a particular type of crop at a specific in a specific area. So obviously, if you're growing different crops, you have to compare the correct crop type too, in order to make sure that you're comparing the right profiles. So from there, we can then compare and do what Griffin performed, which is the anomaly detection, which really, if we look at it, it takes a particular snapshot in time. So say today's date, we captured an image, and we calculate the NDVI for today's date after doing the analysis-ready data conversion. And then we want to compare that to the average or max NDVI value for the same Julian date captured across all the previous years where we have historical data. And that creates the baseline, and then we can compare today's imagery to that, where we can, anything in yellow is essentially growing at the expected rate. Anything in red means that it's the KPI is performing below expectation, and green means it's performing above expectation. Now, in terms of the regression analysis, we can do a similar thing where we can take these growth curves for, once again, a particular plot, a particular field, as well as a particular type of crop that you're growing, and you can compare those curves, those growth curves for that plot or for that field, and then from that you would be able to, or you'd also capture the yield that you have in those particular years, so the actual yield. And then from that, you can run that through a machine learning or AI algorithm in order to perform the regression analysis and look at this point in our growth curve, at this period in our season, where are we at and what is the prediction from that compared to all previous years. So if you want to learn, our Catalyst Analysis Ready Data workflow is currently available today in Catalyst Enterprise. It's coming soon to the cloud through our Catalyst microservices, so it'll be on a variety of cloud providers such as Up42. We'll be bringing it to a variety of cloud providers soon. And if you want to learn more about our analysis-ready data technology, come visit our website at catalyst.earth, and you can go to technology/ARD. So we look forward to hearing from you and, of course, addressing some of your questions now live.
Thank you, gentlemen. Thank you for that great presentation. We definitely had quite a few questions coming in, but as you mentioned, Sean, some of them you actually just answered in your conclusion, but let's maybe go ahead and clarify again in case people didn't catch it. So one question that came in was related to precision farming being something for a huge scale farmer. What do you think about how deep learning and satellite data can help small-scale farmers?
Yeah, and I think it's actually a very valuable application for small-scale farmers. So in terms of precision farming and identifying where within a crop, so the anomaly detection that we showcase, that you would have to use very high-resolution imagery, and it may not have as much value on very small-scale farms. But in terms of the predictive analysis and doing understanding how your field is performing at a particular period in time compared to historical data when you're growing a specific type of crop, that is valuable across the board, whether it's small scale or large scale. And we work with a lot of small scale farms, for example, in Taiwan, where there's a lot of micro farming going on, as well as they have a growth season all throughout the year. And they're growing, one plot is growing a variety of different types of crops at different times of the years, and it's very unpredictable. So it's still able to leverage, so long as you know and you keep an inventory of your growth curves versus and the type of crop you're growing at a particular time, you're able to still leverage this information and help use it for predictive analytics. Instead of using Julian days, you would use it from a start date based on the phenology of that plant.
Thanks again, gentlemen, for your presentation. Keep in mind that the data and algorithms shown here today will soon be available on the Up42 marketplace. So stay tuned as the ag tech offerings on Up42 continue to grow. If you haven't already familiarized yourself with the Up42 platform, we have an intuitive user interface where you can click together all types of geospatial data with off-the-shelf algorithms in a workflow and get immediate insights. You could actually go there now and test it yourself and even download some weather data from Mediamatics with just a few clicks. You can claim your complimentary 10,000 free credits on the Up42 platform by clicking the button that will be shown on the screen. And those credits can be used for any open source data, all types of vegetation indices on Sentinel-2, and much, much more, even beyond just agricultural use cases. As you can see on the slide behind the sign up, there's lots of different, you can also purchase high resolution data with us and even run off the shelf machine learning algorithms and even create bespoke solutions with our Python SDK. But for more on this, just contact our sales team. Last, but certainly not least, we also invite you to join us on April 8th at 4 p.m. CEST, be mindful of the daylight savings time, to take a deeper look at the first Catalyst microservices to be deployed on Up42, the Catalyst INSAR stack workflow, which can detect and calculate the velocity of ground movement up to a few millimeters. This is a workflow ideal for monitoring infrastructure, mining, construction, public safety, etc. So check the link in the chat for more details. If you have further questions that we didn't get around to answering today, don't worry. Our team at Up42 will be in touch, and you can feel free to ask your questions then. Again, thank you all so much for coming, and hope you all stay well. For more ideas on how to upgrade your agricultural workflows or just your geospatial analytics overall, come visit us at up42.com.